In mathematics, complex integer sequences can scale endlessly toward infinity, all while maintaining strictly rigid internal geometric symmetries. This formula represents a specific reciprocal quadratic family. A reciprocal quadratic is a polynomial structure where substituting the variable with its reciprocal creates a symmetric relationship. In this case, every coefficient is defined strictly by a sequential Fibonacci number. At the 10th iteration, where n equals 10, the variables morph into their actual Fibonacci values. The equation becomes 144x squared minus 89x minus 55 equals 0. Every quadratic equation has a discriminant, the value that dictates the behavior of its roots. For this specific equation, the discriminant bracket scales rapidly, reaching a value of 436,231. This large number sits in direct contrast to another property of the polynomial, its Vieta trace. The Vieta trace is the mathematical sum of the equation's roots. If we take this quadratic and physically swap its boundary terms, the leading coefficient and the constant, the new equation possesses an exact, simple Vieta trace of exactly -714. How can a polynomial defined by such a massive escalating discriminant perfectly encode a simple, unchanging root sum across its boundaries? These two properties are tied together by a formal algebraic bridge. By building that bridge, we can prove that the normalized discriminant bracket exactly recovers the lower Vieta trace. We begin with the first component of our proof, the left pillar. Our focus here is on manipulating the original quadratic equation. To isolate the core properties of this family, we need to convert it into a monic equation, a polynomial where the leading coefficient is exactly 1. We achieve this by multiplying the entire equation by the term x squared times fn. With a leading coefficient of 1, we can now calculate the formal discriminant of this new monic quadratic. Expanding these terms reveals the interior structure of the formula and exposes a common factor of fn across the entire expression. By factoring out fn, we successfully isolate the core operational unit driving the polynomial. We formally define this isolated section as the discriminant bracket, labeled kn. To ground this in our n equals 10 example, we plug the integers back into this kn bracket. Calculating 55 times 89 squared plus 4 times 144 outputs precisely 436,231. This allows us to analyze the structural properties of the sequence without the distraction of its raw arithmetic size. We can break kn down even further using the Lucas residual identity. A Lucas sequence follows the same additive rule as Fibonacci, but it begins with 2 and 1 instead of 0 and 1. To simplify the algebra, we substitute the sequential Fibonacci variables with basic placeholders, defining a as fn-1 and b as fn. The subsequent Fibonacci numbers are then redefined as combinations of a and b. We then expand the kn difference using these new placeholders. The expanded equation factors into two distinct polynomial groups. We resolve the quadratic portion on the right using Cassini's identity. This rule proves the product of adjacent Fibonacci numbers differs from the square of the middle number by exactly 1 or -1. Because of Cassini's identity, that entire right-hand section of the equation collapses into the alternating constant of -1 to the power of n. We are left with the linear term a plus 3b, which we resolved by mapping it back to the sequence definitions. Algebraically, a plus 3b aligns with the Lucas sequence, translating directly to ln plus 1. By dividing the original kn expression by the squared boundary term, we arrive at the normalized extractor formula shown here. Applying our n equals 10 variables to this specific structure means we are calculating 436,231 divided by 144 squared. The normalized bracket perfectly extracts a lower Fibonacci rung, fn-2, while simultaneously isolating a predictable alternating Lucas residual. With the discriminant isolated, we move to the right pillar of our proof, the equation's roots. To establish a universal rule, we define a generic reciprocal quadratic family, replacing the Fibonacci numbers with the standard parameters a, b, and c. We convert this generic form into a monic equation by multiplying the polynomial by c times x squared. This exposes the linear coefficient, mathematically defined as b times c. According to Vieta's formula, For any monic quadratic, the sum of its roots is exactly the negative value of that linear coefficient. Now we execute the boundary swap, physically trading the leading coefficient a and the constant term c. When this swapped equation is translated into monic form, its linear coefficient becomes c times b. Because multiplication is commutative, c times b is identical to b times c. The Vieta trace remains unchanged. We can connect this rule directly to our n equals 10 Fibonacci numbers. Here are two distinct polynomial equations defined by the sequence. We execute the same operation, swapping the outer boundary parameters. To find the shared root sum, we multiply the b and c equivalents, which are 34 and 21. Any two reciprocal quadratics related by this specific boundary swap are anchored by the same root sum, resolving perfectly to negative 714. Here is the Bridge Theorem. On top, the normalized Lucas residual extractor. On the bottom, the invariant Vieta trace. First, subtract the residual terms to isolate the fn-2 component. Next, multiply this expression by fn-1. This maneuver outputs the exact product of fn-1 and fn-2. That product is exactly the formula for the invariant Vieta trace, derived from our boundary swap. Applying this to the n equals 10 example from our introduction, we replace the variables with their integer counterparts. Step by step, the arithmetic resolves. The large fraction simplifies to exactly 21. We are left with a final multiplication, 34 times 21. The equivalence is exact. The complex discriminant bracket collapses to 714. The 714 anomaly is a specific output of this algebraic bridge. This equivalence proves that the massive discriminants and simple traces of Fibonacci quadratics are tied directly to the core properties of the Fibonacci and Lucas sequences.